Today we're going to be discussing, moving on in and discussing an easier way to reduce expressions into canonical form using what are known as Karnaugh maps or K-maps. Or just K-maps. K-maps guarantee, if done properly, guarantee a properly reduced expression. You shouldn't be able to reduce the expression any further after using a K-map properly. We'll start with a 2x2 map. Say you have X and Y, two variables, and you have 0, and you have 1, 0, 1, 1, just as an example. And that's your state table that you're trying to create a expression for. So you make a map with 4 boxes, and where the values are here, you put the output in the box. So 0, 0 is a 1, 0, 1 is a 0, 0 on the X, Y is 1, put a 0 here, X is 1, Y is 0, put a 1 for this one, and 1 and 1 here. Okay, now what does that give us? Well, you have these groups of one. You group the ones together. Let me use a different color for that. Oh. In powers of 2. So you group them in powers of 2. So you can group them in group by 1s, 2s, 4s, 8s, 16s. They don't get any bigger than that unless you're using a computer to generate multi-dimensional K-maps. But anyway, so you do the largest groups of powers of 2, and then you see what makes those groups 1. So in this case, this is X, and this is Y. This is Y prime. This is X prime. So this is just X. Because the Y doesn't matter. The X is always 1. So it simplifies to just x. Here, it's y prime. It doesn't matter what x is. If it's y prime, it's a 1. So you do an or y prime. So that is the basics of how you use a K-map. You group by the largest power of 2. Now, if you change your output to, say, 0, 1, 1, 0, recognize that as a XOR gate right off, I'm sure. But 0, 0 is going to be 0. 0, 1, 0, 1 is going to be a 1. 1, 0, 1, 0 is going to be a 1. And 1, 1 will be a 0. Now in this case, you can't group by a group of 2. So you have to just group by the 1s. And you see that the expression is x and not y. Oops. And y, x, not x, and y. So that would be the, using and, ors, and nots, the expression for the XOR gate. You can work through all the 16 combinations of functions that you can do with 2 variables, like we did before the break, and see that it simplifies to the various expressions that you get. Now, if you move up to 3 variables, let's see here. And your out is like so. Let's say 1, 1, 0, 1, 0, 0, 1, 1. Just making these up as I go along here. You have 3 variables, 8 combinations. So with 3 variables, you make a map with 8 squares. And do x, y across the top and z on down the side. Let me. Now, labeling the map this way you go across the top, changing one bit at a time. So you start out with 0, 0, x is 0, y is 0. Change one bit, x is 0, y is 1. Change one bit that's not going back to 0, 0, makes it 1, 1, not 1, 0. That would be changing 2 bits. And then change one bit again to be 1, 0. So you have all combinations of x and y across the top. Z, again, 0, 1. Changing one bit at a time. Now, you can look at these as the binary numbers here. 0, 1, 2, 3, 4, 5, 6, and 7. And you would put those in the proper square on the K map. So this would be 0, 0, 0, 1, 1, 0, 1, 0, 2, 0, 1, 1, 3, 0, 1, 1, 1, 1, 0, 0, 4, 1, 0, 1, 1, 0, 1, 5, 1, 1, 0, 1, 1, 0, 6, and then 7 would be 1, 1, 1 here. So this might be presented to you as a sum of 0, 1, 3, 6, 7. And you just drop your ones in the appropriate spots. So 0, 1, 3, 6, and 7. And then fill in the rest with zeros. All right, here we have opportunities to group by powers of 2. You would not have a group of 3. That wouldn't work. Only group by powers of 2. And you can overlap like so. Those are your powers of 2. Groups by powers of 2. Now, if you look at this, this is your y, because y is 1 there. Your z is going to be, or I'm sorry, your x will be here, because x is 1 in both of those spots. And then z right here. And then this would be z prime, y prime, y prime, and x prime. Okay? Then you would do your terms based on your grouping. So y prime z. I'm sorry. Y prime. This is all in y prime, and it's all in x prime. Z doesn't matter, so it's x prime, y prime for this group. This is all z and all y, so yz for this group. And then finally, you have x and y. It's all in y, all in x. Z doesn't matter. So x, y. You see how that happens? So you do your groups by your ones, adjacent groups of ones in groups of the size of a power of 2. Okay? Now let's look at a slightly different one. I'm not going to bother with a truth table on it. Keep that the same. And I'm going to do 1, 1, 1, 1. Now this poses an interesting situation. While it looks like that two groups of 2, there's actually a group of 4. Because there's only one bit difference between this one and this column and this column. These can wrap around, making a group of 4. You want the larger groups. That reduces the number of literals in the term. So this one would be y prime. I erased the so all these are in y prime. Z doesn't matter. X doesn't matter because the ones are in both x and x prime, and they're both in both z and z prime. So the final expression is just y prime, because it wraps around. And you can do similar things with groups of 2. With the groups of 4, though, it's groups of 4 can be a square or a line. So you have two groups of 4 here. You have the one we had before and a lined group of 4. You cannot do groups of 4 in an L-shaped pattern, only in squares and in lines. So this one would be the y prime from we got before, and or I should say this group is all in Z, so y doesn't matter, x doesn't matter, so it's all in Z. So it'd be y prime Z, y prime or Z. Making sense? Going too fast? Going a little fast? No? Okay. You can wrap groups of 2, you can wrap groups of 4, 8, what have you. Let's see here. The larger the group, the fewer the literals in each term. So I'm going to erase this. And we'll do an example and get feedback from the audience. So we got, let's say 1, 1, 1, 1, 1. What would our first group be? What would your first group be? So you're pointing y and y prime, this one right here? Okay, yeah, that works. X prime to x, these two? Okay. Yeah. What about this lonely one over here? I'm sorry? They're both in y prime. This one is in y prime with this one. So this can be grouped that way. Wrap around. Z prime and y prime. So we'll start with that group. Z prime, y prime, z prime. Because the x doesn't matter. These two ones are in z prime and in y prime. So that's a group. What about this group? What would the term be for that group? Z prime what? Z prime x. Exactly. So we'll x z prime that. And this bottom center one? YZ. Yep. And that is your reduced expression for that thing. There's no algebraic manipulation needed to reduce it any further. You could have, not to say that this is a unique solution, you could have also done this group. And you still have all of them covered, and there's still 3 terms. They would be different from, it would be different from this, but it would still be the same number of terms, the same number of literals. So there is multiple completely reduced functions. It's just a matter of taste as to how you want to group your groups. But yeah. All right. Let's try something a little bit more elaborate. Where you have W, X, Y, Z out. Let's see if I can do this in one column. I can count in binary. Really, I can. It's not going to work. So we'll do out there, and we're on 1. Okay. And out again here. So we have 16 inputs, or 16 combinations of inputs. What would the configuration of the K-map be, do you think? Any guesses? Well, it would be one big square. 4x4 K-map. So divided by 4. And then, of course, label them across the top. Start with 0, 0. Change 1 bit. Change 1 bit. Change 1 bit. Same thing going down the sides. 0, 0. 0, 1. 1, 1. 1, 0. And let's give some outputs here. 1, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1. Okay, just some random inputs there. So your numbers are going to be, that'll be fine. So where your number one's going to be? Where your one output's going to be? 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 1 is going to be a 1. 0, 0, 1, 1 is going to be a 1. 0, 0, 1, I'm sorry, next is 0, 1, 0, 0. 0, 1, 0, 0 is going to be a, oh, it's going to be a 0, yeah. 0, 1, 0, 1, 0, 1, 0, 1. 0, 1, 1, 0, 0, 1, 1, 0 is there. 0, 1, 1, 1 is a 0. And all the way over there, 1, 0, 0, 0. 1, 0, 0, 0. No. 1, 0, 0, 0 is a 0. 1, 0, 0, 1. 1, 0, 0, 1. 1. 1, 0, 1, 0 is a 1. 1, 1, 0, 0 is a 1. 1, 1, 0, 1 is a 1. 1, 1, 1, 0. 1, 1, 1, 0. And 1, 1, 1, 1 is a 1. And these are zeros. Okay. So, how many groups do we got? Groups of powers of 2. 1, 2, 4, 8, 16. Let me do this is the x and x prime. And this is W. And this is W prime. And we have Y prime. And we have Z and Z prime. Z prime. Okay. Where would we have some groups? Whole first column, yeah. All right. Any other groups of 4? Across the second row? Third column? The bottom right? Grouped with what? I'm sorry? It can go either way. It could go this direction or wrap around the sides. So there you go. So what would the term for this one, for this first column, what would it be? X prime, W prime, X prime. Yep. The third column. I think I heard a WX. Yeah. WX. Because they're all in the W and all in the X. Y's don't matter, Z's don't matter. What about this second row here? Y prime Z. I heard that. And then this here, the 2 group. WZ prime, but it's not all of Z prime. It's the Z prime that's in the Y. So it's all in the Y, all in the Z prime, all in the W. So it would be W, Y, Z prime. X doesn't matter because it's in both X and X prime. So on a 4x4 K-map, a group of 2 is 3 literals. A group of 4 is 2 literals. Group of 8 would be 1 literal. Yeah. So didn't get a group of 8 on this one, but it would be possible. Yes. If these 2 columns were together, if it were just the first and the second column, it would be Y prime or W prime only, because it's in both X and X prime, both Y and Y prime, and in Z and Z prime. So if the 2 columns were together, it would be just 1 literal. So let's get one that has some wrapping here. Let's do this with the same one with adding this one here. Now, how would that group? Yes, you could wrap both direction, up and down. So as well as side to side. So it would be wrapped like this. So what would the expression, what would the term be for that one? They're all in Z prime. And they're all in X prime. So it would be, and Y doesn't matter because it's got some in Y and some in Y prime. W doesn't matter because you have some in both. So it would be X prime, Z prime. Yeah, that works. Yeah. And so you can get go from a state table or a expression with a summation. The sum symbol and create your K-map and reduce it down to a not necessarily unique, but a minimized expression. Minimum number of literals, minimum number of gates. So it is theoretically possible to do 5 variables, but you need 3-dimensional space to do that, and you can't do that on a whiteboard. Computers can do it, and you can group. You can get into nth dimensional space with the with increased number of inputs, but for the purposes of this class, going to 4 inputs is definitely sufficient. We will get into next time we will get into doesn't matter or don't care conditions. So we will get into that on Thursday, do some more examples, and I should have some homework to hand out to you on Thursday so you get some practice working with the K-maps. So look forward to that. I guess have a good day. See you on Thursday.